Look up at the night sky, past the familiar constellations and the glow of the Milky Way, and you'll find something extraordinary lurking just beyond the edge of our galaxy. A cosmic neighbor so strange, so full of secrets, it defies everything we thought we knew about the universe. The Large Magellanic Cloud isn't just another collection of stars. It's a puzzle box of cosmic anomalies, a place where the laws of physics seem to bend and where mysteries lurk in every corner. From celestial objects that shouldn't exist to forces we can't yet explain, this satellite galaxy is a treasure trove of the bizarre, and today we're diving deep into its most mind-bending enigmas. Imagine a place where stars vanish without a trace, where entire regions of space flicker like a dying light bulb, and where strange, luminous structures stretch across the void with no clear explanation. The Large Magellanic Cloud isn't just challenging our understanding of space, it's rewriting it. Some of these phenomena are so unusual that even the most brilliant astronomers are left scratching their heads, questioning whether we've missed something fundamental about how the cosmos works. And the closer we look, the more questions arise. What's causing these cosmic oddities? Are they natural, or could they hint at something even more extraordinary? That's exactly what we're about to explore. Over the course of this journey, we'll uncover 30 of the most baffling, awe-inspiring, and downright eerie phenomena hidden within the Large Magellanic Cloud. Each one is a story, a cosmic riddle waiting to be solved. Some might be keys to unlocking the universe's greatest secrets, while others could remain mysteries for generations to come. So buckle up, because we're about to venture into one of the most enigmatic corners of space, where every discovery raises new questions and where the universe, as always, refuses to make things easy. The answers, or the lack of them, might just change how you see the night sky forever. The Tarantula Nebula isn't just another stellar nursery, it's a cosmic factory operating at breakneck speed, churning out stars at a rate that defies everything we thought we knew about how these celestial giants are born. Officially catalogued as 30 Dwarfs, this turbulent region in the Large Magellanic Cloud is the most intense star-forming hotspot in our entire galactic neighborhood, a place where the rules of star birth seem to warp under extreme conditions. Here, massive stars, some weighing over 100 times the mass of our Sun, form in dense clusters, packed so tightly together that their collective glow outshines entire galaxies. But what makes the tarantula truly baffling isn't just the sheer number of stars being born, it's the way they're forming. Most star-forming regions, like the familiar Orion Nebula, follow a relatively predictable script. Gas clouds slowly collapse under gravity, fragmenting into smaller knots that eventually ignite into stars. But the tarantula operates on chaos. Hubble's sharp eye revealed intricate webs of gas and dust twisted into bizarre pillars and cavities, sculpted by hurricane-force stellar winds and blistering radiation from newborn stars. Then came the James Webb Space Telescope, peeling back even more layers of the mystery. Its infrared vision exposed vast networks of turbulent filaments, structures so dense and tangled that they shouldn't exist under current models of star formation. Some regions appear to be birthing stars 10 times faster than theories predict, as if some unseen force is turbocharging the process. Astronomers are scrambling to explain what's happening. Could it be the nebula's unique chemistry, rich with heavier elements from previous stellar explosions? Or is the tarantula's gravitational environment, nestled in a small galaxy with less overall pull, somehow allowing gas to collapse more easily into stars? Then there's the eerie presence of rogue stars, massive fugitives flung from their birth clusters at terrifying speeds, leaving behind trails of shocked gas. Every answer only leads to more questions. What's certain is that the Tarantula Nebula isn't just an outlier, it's a challenge to our fundamental understanding of how the universe builds stars. If conditions here were more common in the early cosmos, as some suspect, it could rewrite the story of how galaxies lit up the darkness after the Big Bang. For now, this fiery cauldron of creation remains one of the most compelling puzzles in the Large Magellanic Cloud, a place where the universe seems to be showing off just how little we truly know. In one of the quietest corners of the Large Magellanic Cloud, something sinister lurks, an invisible river of darkness so vast it swallows starlight whole. Stretching across thousands of light years, this eerie dust lane, nicknamed the Dark River, isn't just another cosmic cloud. It's a phantom, a ghostly structure so dense it blots out entire star clusters behind it, leaving astronomers to piece together its secrets through the absence of light. When telescopes first scanned this region, they saw only gaps in the sky chasms where stars should have been. But with the arrival of infrared eyes like Spitzer, the truth emerged: this wasn't empty space. It was a colossal, creeping shadow, a ribbon of dust so thick and cold it defied explanation. The Dark River's origins are as murky as its appearance. One leading theory suggests it's the skeletal remains of a dwarf galaxy, torn apart in a violent collision with the Large Magellanic Cloud long ago. If true, this would make the dust lane a cosmic gravestone, the lingering aftermath of a galactic murder. Supporting this idea are strange chemical signatures, elements like carbon and silicon, locked within the dust in proportions unlike anything else in the LMC. But there's another, even wilder possibility. The Dark River might be a freak of nature, a molecular cloud so massive and dense it shouldn't exist in a small galaxy like this. Normally, such structures are found in sprawling spirals like our Milky Way, where gravity has eons to sculpt gas into these monstrous filaments, yet here it sits, an anomaly defying the rules. Spitzer's infrared vision peeled back the darkness, revealing tendrils of dust weaving through the LMC like veins. Some sections appear twisted, as if some unseen force had wrung them like a wet towel. Others stretch unnervingly straight, their edges knife-sharp against the glow of background stars. And then there are the void's pockets where the dust thins abruptly, as if something had blown bubbles in the river's depths. These bizarre features hint at turbulent pasts, perhaps ancient supernova shockwaves or the gravitational kicks of passing star clusters. What makes the Dark River truly unsettling is how it challenges our understanding of dust itself. In most galaxies, dust is a nuisance, a dimming fog that obscures our view. But here, it's the main character, a structure so dominant it reshapes how light travels through its corner of the universe. Some astronomers wonder if similar rivers once slithered through the early cosmos, playing a hidden role in how galaxies grew. Others suspect it's feeding the Tarantula Nebula, its dusty tendrils funneling raw material toward that stellar factory. But for now, the Dark River keeps its secrets, a serpent of shadow reminding us that sometimes the universe's most profound mysteries aren't in the light, but in the darkness between. Among the twisted wreckage of ancient stellar explosions in the Large Magellanic Cloud, one supernova remnant stands out not just for its violence, but for its sheer defiance of cosmic motion. N49 isn't merely a scar left behind by a dying star, it's a rebel, hurtling through its own galaxy at speeds that make astronomers do a double take. Most remnants expand evenly from their birthplace, like ripples in a pond. But N49 is different. This tangled web of glowing gas and shockwaves is racing against the natural rotation of the LMC, as if some unimaginable force kicked it sideways with enough power to send it careening across the cosmos. The mystery begins with the remnant's bizarre shape. Hubble's iconic images reveal a chaotic landscape of filaments, some stretching like stretched taffy, others coiled into knots of glowing plasma. But it's the Chandra X-ray Observatory that exposed the real enigma. N49's brightest region isn't at its center, where theory says it should be. Instead, the X-ray glow is lopsided, concentrated toward one edge as though the entire structure had been shoved violently off balance. The leading explanation: this might be the handiwork of a kicked neutron star, a cosmic cannonball forged in the supernova's heart and launched into space by asymmetrical forces during the explosion. But the plot thickens. Deep within the remnants wreckage, astronomers found something even stranger: a neutron star spinning wildly, its magnetic field tangled into a configuration unlike anything ever seen. Typical neutron stars have orderly magnetic poles, but this one's field lines are scrambled, possibly twisted by the very forces that sent it flying. Some theories suggest it wasn't alone when it exploded. Could N49's progenitor star have had a hidden companion whose gravity influenced the blast, turning the supernova into a cosmic slingshot? Or was the explosion itself so lopsided that it sent debris flying in one direction like shrapnel from a grenade? Then there's the magnetic mayhem. Radio telescopes have mapped N49's magnetic fields, revealing patterns that look less like orderly lines and more like a spiderweb caught in a hurricane. Some regions show fields so tightly wound they're practically braided, while others appear stretched thin, as if the remnant is dragging magnetic threads across the galaxy. This isn't just a remnant, it's a laboratory for extreme physics, a place where the rules of magnetism warp under conditions we can't replicate on Earth. Every clue raises new questions. If neutron stars can be kicked across galaxies, how many others are out there, drifting unseen? Could N49's rogue motion explain similar remnants elsewhere in the universe? For now, this runaway remnant keeps its secrets, a celestial fugitive reminding us that even in death, stars can still defy expectations. Hidden in the faint glow of the Large Magellanic Cloud, a ghostly sphere of high-energy radiation pulses silently across the cosmos, an enigma so vast it dwarfs entire star systems. LMC N79 isn't just another cosmic structure. It's a gamma-ray bubble stretching over thousands of light-years, a relic of some cataclysmic event so powerful its echo still ripples through space. Discovered by the Fermi Large Area Telescope, this faint but colossal structure defies easy explanation, lurking at the edge of detection like a whisper from the universe's most violent past. What makes LMC N79 so baffling isn't just its size. It's the energy signature. Gamma rays, the universe's most potent form of radiation, typically come from extreme sources like pulsars or supernova remnants. But this bubble emits them diffusely, like a fading afterglow with no clear central engine. Some astronomers suggest it could be the tomb of an ancient quasar, a relic from when the LMC's core blazed with the fury of a supermassive black hole feasting on matter. If true, it would mean this small galaxy once hosted a beast rivaling those at the hearts of giant galaxies, something current models say shouldn't be possible. Then there's the dark matter angle. Simulations show that dense regions like the LMC could theoretically trap dark matter particles, causing them to annihilate each other in bursts of gamma radiation. LMC N79's smooth, spherical shape fits this eerie scenario, a slowly dissipating cloud of energy from invisible particles colliding over eons. But the most tantalizing theory, a hypernova, not just any stellar explosion, but one of the rarest, most violent events in the universe. A star so massive its death throws unleashed a jet of energy powerful enough to carve this bubble into space. If confirmed, it would be the first evidence of such an event outside our own galaxy. Compare this to the Milky Way's Fermi bubbles, twin towers of gamma rays stretching above and below our galactic plane. Those structures are younger, more energetic, and clearly linked to our supermassive black holes' past eruptions. LMC N79, by contrast, feels ancient, its edges softer, its story murkier. While our galaxy's bubbles scream of recent violence, this one murmurs of forgotten chaos, a puzzle missing half its pieces. The deeper astronomers look, the more questions arise. Why is the bubble's interior oddly devoid of stars? Could its expansion have swept the region clean? And why does its gamma-ray glow flicker slightly, as if whatever created it left behind a dying ember still sputtering energy into the void? For now, LMC N79 remains a cosmic riddle, a shadow of something unimaginably powerful, and a reminder that even our closest galactic neighbor holds secrets waiting to rewrite the rules of astrophysics. Scattered across the Large Magellanic Cloud like cosmic misfits, a peculiar population of stars burns with an intense blue hue, standing starkly out of place. These aren't your average young, hot stars nestled comfortably within stellar nurseries. These are the blue outliers, lonely, blazing anomalies that defy expectations by existing in the quiet voids between star-forming regions, far from the dense clusters where stars like them should reside. Their very presence challenges our understanding of how stars are born and how they move through the cosmos. Spectroscopic analysis reveals just how strange these stars truly are. Their surfaces are loaded with helium and nitrogen, telltale signs of massive stars that have burned through their hydrogen fuel at a furious pace. But here's the twist: their chemical profiles don't match the typical composition of stars formed in isolation. Instead, they look like refugees from dense stellar clusters, places where gravitational tugs and violent interactions could have flung them into the void. The leading theory: these stars were once part of tight-knit stellar families until a gravitational brawl ejected them at staggering speeds, sending them careening across the galaxy like cosmic castaways. Yet not all blue outliers fit this runaway narrative. A handful show chemical signatures hinting at a far more puzzling origin: stars that may have formed alone in the quiet darkness between star-forming clouds. This idea upends decades of stellar formation theory, which holds that massive stars need the dense, turbulent environments of nebulae to collapse and ignite. If confirmed, it would mean the universe has a secret, lonelier path to starlight, one we've barely begun to understand. Then there's the wild card: stellar collisions. Some blue outliers exhibit bizarre abundances of heavy elements, suggesting they might be the products of two smaller stars merging into one massive hot powerhouse. This rare process, normally seen in the crowded cores of globular clusters, shouldn't happen in the sparse outskirts of the LMC, but the evidence is written in their light. What binds these stars together is their defiance. Whether runaways, loners born against the odds, or the remnants of violent mergers, they force us to reconsider the rules of stellar life cycles. Each one is a clue, a piece of a larger puzzle about how stars move, interact, and sometimes break free from the cosmic script. And as telescopes uncover more of these blue enigmas, one thing becomes clear: the Large Magellanic Cloud is a far more dynamic and unpredictable place than we ever imagined. Just half a light year away from one of modern astronomy's most famous supernovas, something even stranger lurks: a cosmic mimic playing a deadly game of disguise. Near the remnants of SN 1987, a peculiar object has been caught in a bizarre cycle of brightening and fading, erupting with the fury of a stellar explosion every few years, only to cool down and repeat the act. This isn't a true supernova; those are one-time, catastrophic events. Instead, it's what astronomers call a supernova imposter, a celestial enigma that blurs the line between routine stellar flares and genuine destruction. Hubble's decades-long vigil has captured this performer in action. Time-lapse sequences reveal eerie, concentric rings of gas expanding outward, the aftermath of violent outburst where the star hurls massive shells of material into space without fully self-destructing. Each eruption dims the star temporarily, as if it's catching its breath before the next act. The leading suspect, a hypergiant star so unstable it's essentially coming apart at the seams. Imagine a pressure cooker with a faulty valve, sporadically blasting steam into the room without exploding. In stellar terms, that's what might be happening here: a star shedding its outer layers in fits of cosmic indigestion. But there's a twist. Some researchers argue the data points to something more exotic: a vampire star system. Picture a pair of stars locked in a deadly dance, where one siphons material from its companion until the stolen gas reaches a critical mass, igniting periodic thermonuclear eruptions on the thief's surface. This could explain the regularity of the brightening events, as the feeding and bursting follow a predictable cycle. Spectroscopic clues add fuel to the mystery, showing chemical fingerprints of fresh helium and hydrogen in the ejected material, elements you'd expect from a star being slowly cannibalized. What makes this imposter especially puzzling is its proximity to SN 1987A. The two objects share the same neighborhood, yet their behaviors couldn't be more different. One died in a single spectacular blast, while the other teases destruction over and over. Could they be related? Some speculate both were part of the same star-forming region, born under extreme conditions that set them on divergent paths, one toward rapid collapse, the other toward prolonged tantrums. The real puzzle is what happens next. Most supernova imposters eventually do explode for real. Their repeated outbursts are often death throes, a star's final protests before the inevitable. If that's the case here, Hubble's watchful eye might soon witness something unprecedented, the moment a cosmic pretender finally becomes the real thing. Until then, this erratic performer keeps astronomers guessing, a reminder that even in the aftermath of a supernova, the universe still has surprises up its sleeve. Buried in the depths of the Large Magellanic Cloud, something invisible tugs at the fabric of space itself, not with light but with pure gravitational muscle. Astronomers call them dark globular clusters, celestial ghosts that defy everything we know about these ancient stellar families. Normally, globular clusters are among the most dazzling objects in the universe, dense balls of hundreds of thousands of stars gleaming like cosmic chandeliers. But they're empty, or at least they appear to be. Their gravitational pull betrays their presence, warping the paths of nearby stars and bending light like a lens. Yet when telescopes peer at their expected locations, they find nothing. No stars, no gas, just darkness. The first hints emerged when sensitive instruments detected subtle distortions in star motions near the LMC's outskirts, ripples that suggested massive, compact objects lurking unseen. Follow-up observations deepened the mystery. Whatever these things are, they weigh as much as typical globular clusters, packing the mass of 100,000 suns into regions just a few dozen light-years across. But unlike their luminous cousins, they emit no light across any wavelength, not visible, not infrared, not even radio. It's as if the universe forgot to fill them with stars. So what could they be? One chilling possibility is that we're looking at clusters made almost entirely of dark matter. Structures where exotic particles clumped together in the early universe, never igniting into stars. If true, they'd be the first pure dark matter objects ever discovered, offering a direct glimpse into the invisible scaffolding that holds galaxies together. But there's a competing theory, equally wild. These might be the skeletal remains of normal globular clusters, their stars ripped away by the LMC's tides over billions of years. Picture a grapevine stripped bare, leaving only the twisted tendrils behind. In this scenario, the cluster's dense cores survived the destruction, now drifting like ghosts of their former selves. The Vera Rubin Observatory, set to begin its survey of the southern sky in the coming years, could finally crack the case. Its revolutionary camera will map the LMC with unprecedented precision, tracing the gravitational fingerprints of these dark clusters in finer detail than ever before. If they're dark matter hubs, their gravity should leave distinct patterns in the motions of background stars. If they're tidal relics, Rubin might spot a few stubborn stars still clinging to the core's cosmic survivors, telling the tale of a violent past. What's at stake goes far beyond these enigmatic objects. If dark globular clusters exist, they could rewrite our understanding of how dark matter behaves on small scales, a puzzle that's baffled physicists for decades. And if they're stripped remnants, they'll reveal just how brutal galactic tides can be, tearing apart even the toughest stellar societies. Either way, these invisible giants remind us that the universe's greatest secrets don't always glow. Sometimes they hide in plain sight, waiting for us to sense their pull. Stretching across the heart of the Large Magellanic Cloud like a cosmic scar, the so-called Great Rift is no ordinary void. It's a starless chasm so vast it could swallow entire solar systems whole. This gaping wound in the galaxy's disk spans over 5,000 light-years, a ragged trench where starlight fades to eerie darkness. Unlike typical dust lanes that merely dim background stars, this rift appears nearly devoid of matter altogether, a ghostly divide splitting the LMC into uneven halves. Gaia's ultra-precise stellar motion data reveals something even stranger. Stars on either side aren't just separated by distance. They're moving as if the rift itself is an invisible wall, their trajectories bending unnaturally around the emptiness. The leading theory points to a violent past, a gravitational tug-of-war with our Milky Way. Simulations show that during one of the LMC's close passes, our galaxy's immense tides may have peeled away a colossal stream of gas and stars, tearing open this wound in the process. Supporting this idea are the distorted orbits of globular clusters near the rift, their paths stretched like taffy-telltale signs of a gravitational trauma that occurred billions of years ago. But there's a competing, even more dramatic explanation. The rift could be the lingering aftermath of an intergalactic hit and run. Another small galaxy, now long gone, might have plowed through the LMC's disk, its gravity scooping out stars and gas like a cosmic bulldozer. Recent observations add fuel to the mystery. ALMA radio telescopes detected faint traces of cold molecular gas lingering in the rift's depths, far less than expected, but arranged in bizarre, thread-like filaments. These wisps of gas aren't just drifting passively, they're vibrating, as if still reverberating from whatever event carved the void. Even more puzzling is how the rift's edges glow faintly in X-rays, heat signatures with no obvious energy source. Some researchers suggest these could be shockwaves frozen in time, the last echoes of a catastrophe that unfolded when our earliest ancestors were just learning to harness fire. What makes the Great Rift uniquely unsettling is how it challenges our understanding of galactic resilience. Most galaxies heal quickly from collisions, their gravity smoothing out distortions within a few orbital cycles. Yet the LMC's rift persists like an unhealed wound, suggesting something fundamental about its structure, or the violence of its past keeps this scar from fading. Whether it's the ghost of a galactic assault or the fingerprint of the Milky Way's gravitational bullying, one thing is certain. This silent gash in the night sky is a reminder that even in space, some breaks never fully mend. Deep within the turbulent heart of the Large Magellanic Cloud, a black hole dances with its stellar companion in a deadly embrace, but this is no ordinary cosmic duo. LMC X3 doesn't just consume matter, it flickers like a faulty cosmic light bulb, its X-ray emissions flaring and fading in chaotic bursts that defy the predictable rhythms of most black hole systems. While famous binaries like Cygnus X1 in our own galaxy pulse with the steady cadence of a metronome, their X-rays rising and falling as material spirals into their event horizons in orderly fashion, LMC X3 crackles with unpredictability. One moment it's a faint ember, the next it erupts with enough energy to outshine entire star clusters. What makes this flickering so baffling isn't just its randomness, it's the contrast with its jet. Unlike other black holes where jets sputter wildly when X-rays fluctuate, LMC X3's relativistic beam remains eerily stable, like a blowtorch set on low no matter how violently the fire beneath it rages. Normally, jets and X-ray emissions are thought to be deeply connected, two sides of the same coin in the black hole's feeding process. But here they're decoupled, as if the cosmic machinery has a glitch we can't yet comprehend. Chandra's X-ray Observatory has caught these contradictions in action, revealing moments when the jet's power holds steady even as the X-rays drop to near silence, or suddenly flare without any apparent change in the jet's intensity. One theory points to the black hole's messy eating habits. In neat systems like Cygnus X1, gas flows smoothly from the companion star into a tidy disk before vanishing past the event horizon. But LMC X3 seems to be dining in chaos. Its accretion disk might be warped, torn by magnetic fields, or clumped into uneven chunks that crash onto the black hole in fits and starts, triggering erratic X-ray bursts. Another possibility, the black hole's spin is misaligned with its orbit, creating a wobble in the inflowing material that disrupts the usual rhythms. There's even speculation that the companion star itself is feeding the black hole unevenly, its stellar winds gusting and waning like an unreliable faucet. Yet none of this explains the jet's stubborn stability. Some astrophysicists suggest the answer lies in the black hole's magnetic field, a hidden scaffold so strong and structured that it keeps the jet flowing smoothly no matter what turmoil happens closer in. Others propose we're witnessing a rare balancing act. The jet might be drawing energy directly from the black hole's spin, independent of the messy accretion process. If true, it would mean LMC X3 is showing us a new way black holes can power their most extreme outbursts, one we've never seen before. Every flicker holds a clue, a glimpse into the strange physics governing these cosmic monsters. And as astronomers keep watch, they're left with a haunting question. Is LMC X3 an oddity, or are we just beginning to see how varied and how unpredictable black holes truly are? In the tapestry of the Large Magellanic Cloud, where massive stars blaze bright and die young, there's a glaring absence, a cosmic census that doesn't add up. Astronomers call it the red supergiant problem, and it's as baffling as it sounds. These swollen, aging stars, the final phase of stellar titans before they explode as supernova, are vanishingly rare in the LMC compared to what physics says should exist. It's like walking into a forest expecting ancient redwoods only to find saplings instead, and the implications ripple far beyond this small galaxy, challenging our very understanding of how the most massive stars live and die. Take Betelgeuse, our Milky Way's most famous red supergiant. If it were placed in the LMC, it would be an outlier, a rarity among rarities. Back home, stars like Betelgeuse are relatively common. They're ruddy, glow-peppering constellations. But in the LMC, surveys keep coming up short. Current models predict dozens more of these cool, bloated giants than telescopes actually spot. Where did they go? One clue lies in the LMC's metallicity, a fancy term for how much heavy element pollution floats in its gas. Unlike the Milky Way, the LMC is metal-poor, its stars forged from more primordial stuff. This changes how they burn. Lower metallicity means stellar atmospheres stay more transparent, allowing radiation to escape more easily. The result, massive stars in the LMC might skip the red supergiant phase entirely, evolving into hotter, bluer beasts before their explosive ends. But there's a darker twist. Some theorists argue the missing giants aren't missing at all, they're hiding in plain sight. As red supergiants near collapse, their cores become ticking time bombs, shrouded in thick veils of dust and gas they've ejected in their death throes. These cloaks could render them nearly invisible to optical telescopes, blending into the LMC's dusty lanes. Infrared surveys have spotted a handful of these buried candidates, their heat signatures betraying their presence. If confirmed, it would mean we're not just bad at counting red supergiants, we're witnessing a cosmic magic trick, where stars vanish before our eyes by wrapping themselves in their own funeral shrouds. Then there's the supernova connection. Red supergiants are supposed to be the progenitors of type Roman II supernova, yet the LMC's observed supernova rate doesn't quite match the expected tally from these missing giants. Could some be collapsing directly into black holes without the fanfare of an explosion? It's a haunting possibility that the universe's most massive stars might sometimes bow out in silence, leaving no trace but a gravitational shadow. Every observation peels back another layer of the mystery. Are these stars evolving differently than we thought? Are they meeting quieter ends, or is the LMC's unique environment rewriting the rules of stellar old age? For now, the red supergiant problem stands as a glaring gap in our cosmic ledger, a reminder that even the life cycles of stars, things we thought we understood, still hold secrets waiting to unravel. Floating like a celestial soap bubble in the sparse outskirts of the Large Magellanic Cloud, DEML 316 shouldn't exist, at least not in its current form. This planetary nebula, the glowing tomb of a dead star, defies logic with its bizarre anatomy. Not one, but two perfectly nested shells of gas, each expanding at different speeds as if two unrelated stars decided to die side by side in cosmic synchrony. Chandra's X-ray vision peeled back the layers of this riddle, revealing a structure so peculiar it sparked a firestorm among astronomers. Is this a 1 in a billion coincidence, or evidence of stars interacting in ways we've never seen before? The outer shell is a slow-moving fossil, a relic of stellar winds blown gently over millennia by an aging star before it shed its outer layers. But inside it sits a second, smaller shell, younger, hotter, and racing outward at nearly twice the speed. Normally, such double structures hint at episodic outbursts from a single star, but DEML 316's chemistry tells a different story. Spectroscopic analysis shows stark differences in the composition of each shell, like finding two distinct flavors of ice cream in the same scoop. The outer shell is rich in nitrogen, a signature of lower mass stars, while the inner one blazes with oxygen, a marker of a hotter, more massive progenitor. This isn't one star's death, it's two, the leading theory, a cosmic illusion. These stars might never have been true binary partners. Instead, they could have been strangers drifting through the same neighborhood, their deaths separated by tens of thousands of years, a fleeting overlap in deep time. Gravity would have sculpted their ejected gas into this peculiar nesting doll shape, leaving behind a fossilized record of their unrelated demises. But there's a tantalizing alternative. What if one star's death triggered the others? Intense radiation or shock waves from the first explosion could have destabilized its neighbor, hurling it toward an early grave. If true, it would mean stars can orchestrate each other's deaths across light years, like dominoes falling in slow motion. Chandra's images add another twist. Nestled where the two shells intersect, a faint X-ray glow betrays the presence of a shock wave, the aftermath of a violent collision between the two expanding bubbles. This superheated gas is a forensic clue, revealing that the inner shell didn't just expand into empty space. It slammed into the outer shell's wall like a fist punching through tissue paper. The energy from that impact still ripples through the nebula today, distorting its symmetry into a lopsided mess. What makes DEML 316 truly extraordinary is its isolation. Most planetary nebulae cluster in crowded galactic regions, but this one drifts alone in the LMC's hinterlands, a place where stars are sparse and interactions rare. That solitude deepens the mystery. Did these stars somehow find each other against the odds, or does their paired demise hint at unseen threads connecting even the loneliest corners of the universe? For now, this floating enigma remains a cosmic Rorschach test, its twin shells a canvas for our theories, its secrets locked in expanding gas. One thing is certain, in the art gallery of the cosmos, DEML 316 is a masterpiece begging to be decoded. Some stars in the Large Magellanic Cloud aren't just moving, they're fleeing, hurtling through space at speeds so extreme they could cross the entire Milky Way in less than 100 million years. These cosmic fugitives, known as hypervelocity stars, race outward at over 500 kilometers per second, fast enough to escape not just their home galaxy, but the gravitational pull of the entire local group of galaxies. What could possibly propel a star with such violence? The answer lies in one of the universe's most brutal playgrounds, the chaotic core of the LMC, where black holes and supernova act like cosmic catapults. Tracking these runaway stars backward reveals an even stranger story. Some trace back to the LMC's central regions, where astronomers suspect an intermediate mass black hole, smaller than the monsters at galactic centers, but still packing a gravitational punch, could be lurking unseen. Simulations show how a binary star system straying too close to such a black hole might suffer a grim fate. One star gets captured, while the other is flung away at terrifying speeds, like a slingshot releasing its stone. The energy involved is almost unimaginable, enough to accelerate a million-degree ball of plasma to a fraction of light speed in seconds. But not all hypervelocity stars come from galactic cores. A handful point to different crime scenes, the remnants of titanic supernova explosions. When a massive star dies in a lopsided blast, the resulting kick can send its surviving companion careening through space like a billiard ball struck by a cue. These supernova survivors often bear chemical scars, abnormally high levels of heavy elements like oxygen and neon, the nuclear ash of their former partners' explosive deaths. Others show unusual rotation, spinning wildly as if still reeling from the shockwave that launched them. Then there are the wanderers with no clear origin, stars moving so fast they shouldn't exist under current models. Their trajectories don't lead back to any known gravitational disaster zones, raising the possibility of even more exotic explanations. Could they have been ejected during close encounters with massive, unseen structures like dark matter clumps? Or are they intergalactic visitors, hurled our way by chaos in a neighboring galaxy like the Small Magellanic Cloud? The most thrilling possibility is that these hypervelocity stars might be messengers from the LMC's violent past. By studying their speeds and trajectories, astronomers are piecing together a hidden history of gravitational encounters, collisions, near misses, and cataclysmic explosions that shaped the galaxy we see today. Each one is a fossilized record of some ancient cosmic trauma, a clue written in motion. And as new telescopes like the Vera Rubin Observatory begin mapping stellar motions with unprecedented precision, the story of these runaway stars is only getting stranger. Some might even turn out to be invaders from beyond the LMC entirely, proving that in the grand dance of galaxies, no star is ever truly at rest. In the cosmic hierarchy, galaxies like the Large Magellanic Cloud don't travel alone. They're supposed to be surrounded by entourages of smaller satellite galaxies, like a monarch with its court. But when astronomers peer at the LMC, they're met with a glaring contradiction. Where are all the dwarfs? Current dark matter models predict the LMC should host dozens of these tiny companion galaxies, yet only a handful have been found. This cosmic census mismatch isn't just a minor accounting error. It's a fundamental challenge to our understanding of how structure forms in the universe. Dark matter's role in galaxy formation hinges on its gravitational pull, sculpting ordinary matter into vast cosmic webs. According to simulations, clumps of dark matter, known as subhalos, should be swarming around galaxies like the LMC, each one massive enough to anchor a small satellite galaxy of its own. Yet when surveys like the Dark Energy Camera scanned the LMC's surroundings, they turned up empty-handed. The discrepancy is so stark that some theorists have begun questioning whether dark matter behaves differently on small scales than we've assumed. Could these missing satellites imply that dark matter particles interact in ways we haven't accounted for, perhaps bouncing off each other like billiard balls rather than passing through one another like ghosts? But there's another, equally compelling possibility. The satellites aren't missing at all. They might have been devoured. The LMC's wild orbit around the Milky Way suggests a history of violent gravitational encounters, close passes that could have shredded its dwarf companions into stellar streams. Evidence for this lies in the LMC's outer halo, where astronomers have detected faint ribbons of stars that don't belong, ghostly remnants of cannibalized galaxies. If true, the LMC might once have had a rich retinue of satellites, only to consume them over billions of years like a cosmic chronos. Yet even this explanation leaves gaps. Some ultra-faint dwarfs orbiting the Milky Way show chemical signatures linking them to the LMC, suggesting they might be escapees former satellites torn away during a gravitational tug of war with our galaxy. Others could be hiding in plain sight, their stars so sparse and dim that current telescopes miss them entirely. Upcoming instruments like the Rubin Observatory promise to hunt these elusive dwarfs with unprecedented sensitivity, peering into the darkest corners of the LMC's domain. The most radical theory, the satellites never formed at all. The LMC's unique environment, its lower metallicity, its turbulent history might have starved dwarf galaxies of the gas needed to birth stars, leaving only dark matter halos as silent sentinels. If so, the universe's smallest galaxies might be far rarer than we thought, their absence a cosmic quirk written in the emptiness around the LMC. Until we solve this puzzle, one thing is clear: the missing dwarfs aren't just a footnote, they're a challenge to the very framework of modern cosmology. The Large Magellanic Cloud has always been full of surprises, but one of its most perplexing secrets isn't something you can see, it's something you can only feel. According to cutting-edge gravitational measurements, the LMC's dark matter halo isn't just enormous. It's lopsided, sitting at a bizarre angle compared to the galaxy's visible stars and gas. Imagine spinning a dinner plate only to realize the weight isn't distributed evenly, it wobbles unpredictably. That's essentially what's happening here, but on a galactic scale, and the implications could rewrite what we know about how galaxies form and evolve. Gravitational lensing studies reveal the shocking truth. When astronomers mapped the invisible tug of the LMC's dark matter by observing how it bends light from background galaxies, they found something unsettling. The halo's mass doesn't align with the galaxy's luminous disk. Instead, it's tilted by as much as 50 degrees, as if the dark matter is dragging behind like a sluggish shadow. This isn't just a curiosity. It's a direct challenge to the standard model of galaxy formation, which assumes dark matter and visible matter should settle into harmony over time. So why hasn't the LMC's dark matter fallen into line? One compelling theory points to a violent past, a cosmic hit and run. Computer simulations suggest the LMC might have collided with another galaxy billions of years ago, a glancing blow forceful enough to knock its dark matter out of alignment while leaving its stars relatively undisturbed. Think of tossing a stone into a pond. The splash disrupts the water's surface, but the deeper currents remain chaotic long after the ripples fade. In this case, the splash was the merger, and the lingering chaos is the tilted halo we see today. Supporting this idea are faint stellar streams detected around the LMC telltale debris that could be the shredded remains of the unlucky galaxy that crossed its path. But there's a wilder possibility. Some researchers argue the misalignment might be evidence of dark matter behaving in ways we don't yet understand. Most models assume dark matter particles interact only through gravity, moving like silent ghosts. But what if they also feel a faint, unknown force, something that causes them to clump or lag behind ordinary matter? If true, the LMC's lopsided halo could be the first hint of dark matter's hidden complexities, a clue buried in the geometry of an off-kilter galaxy. The stakes are high. If the tilt stems from an ancient collision, it means the LMC's history is far more turbulent than we imagined, a saga written in the language of gravitational recoil. If it's a sign of exotic dark matter physics, we might be staring at the first cracks in a decades-old theory. Either way, this misaligned halo isn't just a quirk, it's a cosmic detective story, one where the culprit's fingerprints are written in the void itself. And as telescopes grow sharper, the LMC's dark matter may yet reveal whether we're witnessing the aftermath of a forgotten galactic brawl, or something far stranger. The heart of the Large Magellanic Cloud pulses with an unsettling quiet, a cosmic library where the loudest voice refuses to speak. At the center of this bustling galaxy, astronomers expected to find the usual chaos, a supermassive black hole feasting on gas, spewing jets of energy, and lighting up the cosmos as an active galactic nucleus. Instead, they've stumbled upon something far stranger, a gravitational giant that refuses to roar. The LMC's core doesn't just lack the brilliant fireworks seen in galaxies like Andromeda or the Milky Way. It's almost eerily muted, as if someone flipped a cosmic off switch. Deep within this silence lurks a puzzle. Radio telescopes have detected the subtle gravitational signature of something massive, likely a black hole weighing millions of suns, yet there's no telltale X-ray glow from an accretion disk, no screaming jets of plasma shooting into space. It's like finding the bones of a dragon but no scorch marks from its fire. One possibility is that this black hole is simply dormant, a sleeping monster waiting for the next cosmic meal. But that raises another question. In a galaxy brimming with gas and dust, how does something so powerful stay hungry? The answer might lie in the LMC's chaotic structure. Unlike the orderly spiral arms of the Milky Way, this galaxy is a tangle of irregular streams and pockets of gas. Simulations suggest its central regions might be too turbulent for stable accretion. Imagine trying to drink from a fire hose instead of a steady river. Gas swirling toward the black hole could be getting shredded by gravitational tides or blown away by fierce stellar winds before it ever gets close enough to ignite the engine. The Hubble Space Telescope spotted hints of this, revealing chaotic gas motions near the core where material seems to be swirling in frantic, uncoordinated eddies rather than settling into a neat feeding disk. But there's a darker alternative. What if the black hole isn't dormant at all, but feeding in a way we can't see? Some models propose it might be slurping up matter in slow, sparse bites, just enough to avoid dramatic outbursts, but too little to produce the telltale fireworks of an active nucleus. The Chandra X-ray Observatory caught fleeting glimpses of faint flares near the core, like a distant campfire flickering in the wind. Could these be the muffled belches of a black hole dining politely, or the last gasps of material slipping past the event horizon in near silence? The implications ripple beyond the LMC. If supermassive black holes can switch between active and silent modes this easily, it could explain why so many small galaxies lack obvious central engines. Perhaps the universe is full of quiet giants, their presence betrayed only by the subtle sway of stars orbiting nothing. The James Webb Space Telescope might soon crack the case, its infrared eyes probing the dusty heart of the LMC for hidden heat signatures or the faint glow of obscured activity. Until then, the galaxy's silent core remains one of its most profound mysteries, a reminder that sometimes the universe's loudest secrets are the ones it refuses to share. Wrapped around the Large Magellanic Cloud like a vast, invisible cloak, its hot gas halo should be a uniform sea of plasma, a scorching atmosphere of ionized particles heated by supernova and stellar winds. Yet lurking within this million-degree shroud is something that defies expectations, a razor-thin boundary where the temperature plummets so abruptly it's like stepping from a sauna into a walk-in freezer. Astronomers call it the cold front, a cosmic weather anomaly frozen in time, and its existence hints at a violent past written in the language of thermodynamics. Chandra's X-ray vision first exposed this bizarre divide, a knife-edge interface where the halo's gas temperature drops by over 50% across a span smaller than the distance between Earth and Alpha Centauri. On one side, particles rage at nearly 3 million degrees. On the other, they simmer at half that heat, separated by what appears to be a shockingly stable barrier. Nothing in physics says such sharp gradients should persist for long heat diffuses. After all, yet this front has endured for millions of years, a thermodynamic fossil resisting the universe's relentless drive toward equilibrium. The leading theory traces this anomaly to a phenomenon called sloshing, typically seen in massive galaxy clusters where gravity's tides churn gas like water in a tilted bucket. When a smaller galaxy falls into a cluster, its gravity displaces the hot gas, creating spiral-shaped cold fronts that ripple outward. the LMC's version might be a scaled-down echo of this process, a relic from when it first plunged into the Milky Way's gravitational embrace. As the LMC orbited our galaxy, its own gas halo could have been yanked backward by tidal forces, creating this lingering eddy of chilled plasma. Supporting this idea are subtle disturbances in the front's shape, kinks and twists that mirror simulations of gravitational sloshing. But there's a twist. Some regions of the cold front show chemical fingerprints unlike the rest of the halo, higher concentrations of elements like oxygen and neon, the nuclear ash of short-lived massive stars. This suggests another possibility. The front might be the corpse of a smaller galaxy that collided with the LMC long ago. As the intruder was torn apart, its cooler, metal-rich gas could have splashed into the halo, resisting mixing like oil floating on water. What makes this cosmic cold snap truly mesmerizing is how it bends the rules of fluid dynamics. Normally, such a temperature discontinuity would erode in mere millennia as particles collide and energies equalize. Yet here it stands, a testament to some unseen force, perhaps magnetic fields threading through the gas, acting like insulation to preserve the boundary. Or maybe the front is continually reinforced by fresh inflows of cooler gas from the LMC's disk, a slow-motion waterfall quenching the halo's heat. For astrophysicists, this isn't just a curiosity, it's a laboratory. Cold fronts in galaxy clusters are well studied, but finding one in a small, irregular galaxy like the LMC suggests these phenomena might be universal, sculpting gas across the full spectrum of cosmic environments. It's also a reminder that even the most diffuse corners of the universe can harbor hidden structure, not just in stars and galaxies, but in the invisible, seething plasma that fills the voids between them. As telescopes probe deeper, this frigid frontier may yet reveal how galaxies bleed heat into the cosmos, and how even the quietest motions can leave scars that last for eons. At first glance, the Large Magellanic Cloud's LHA 120 North 88, better known as the Ring of Fire, looks too perfect to be natural. This stunning loop of ionized gas spans over 500 light-years, a near-symmetrical bubble glowing with the intensity of a cosmic neon sign. Most stellar wind bubbles are messy affairs, their edges frayed and irregular like burst balloons, but this one, it's a celestial halo so precise you'd swear it was drawn with a compass. The secret to its unnatural perfection lies in the heart of destruction. Not one, but multiple supernova detonating in concert, their shockwaves colliding to sculpt this freakishly round cosmic artifact. Peering into the ring's core reveals its architects, a gang of massive O-type stars, each burning tens of times hotter than our Sun. These stellar powerhouses blast their surroundings with ultraviolet radiation so intense it strips electrons from atoms, lighting up the surrounding gas like a fluorescent tube. Yet their most destructive work comes from their winds, supersonic streams of charged particles that howl outward at millions of kilometers per hour. Normally, such winds carve chaotic cavities, but here something extraordinary happened. When these stars began exploding one after another, their combined shockwaves met in just the right way, reinforcing one another to create a shockingly uniform pressure wave that blew the bubble's edges into this uncanny geometric shape. The real mystery isn't how the Ring of Fire formed, but why it hasn't faded. Superbubbles typically dissipate within a few million years as turbulence shreds their delicate structures. Yet this one persists like a fossilized breath in the cosmic wind, its edges unnervingly crisp. One clue comes from its surroundings. The ring sits in a region of unusually dense gas, a celestial moat that may be absorbing external turbulence and preserving the bubble's symmetry. Another theory points to magnetism. Faint magnetic fields threading through the structure could be acting like a cosmic corset, preventing the gas from straying. Then there's the puzzle of timing. The bubble's O stars are all roughly the same age, suggesting they were born together in a single, colossal starburst event. But stellar siblings shouldn't explode in such perfect sequence. Supernovae are chaotic by nature. unless perhaps these stars were nudged toward destruction by some unseen force. A passing dark matter clump, gravitational kicks from a hidden black hole, the possibilities spiral as wildly as the bubble's own flawless curves. What makes the Ring of Fire more than just a cosmic oddity is what it reveals about stellar teamwork. Most massive stars live solitary lives, their deaths isolated tragedies. But here, their combined fury created something greater than the sum of its parts, a structure so finely balanced it walks the line between order and chaos. As telescopes probe deeper, this fiery loop may yet teach us how stars communicate across light years, turning random violence into unexpected art. And for astronomers, that's the most dazzling flame of all. Most galaxies spin with a kind of cosmic choreography, their stars swirling together like dancers in a grand celestial ballet. But peer closely at the Large Magellanic Cloud, and you'll spot rebel stars that move to their own rhythm, orbiting against the galaxy's natural spin. These backward wanderers aren't just breaking the rules, they're forcing astronomers to question how galaxies like this one came to exist in the first place. Are they invaders from another galaxy, or remnants of a violent cosmic collision written in the star's rogue motions? The first clues emerged from painstaking measurements of stellar velocities. While the majority of the LMC's stars obediently follow the galaxy's clockwise rotation, a small but significant fraction, about 1 in 20, defy the flow, tracing stubborn counterclockwise orbits. Their paths aren't just slightly off-kilter, they're full-fledged reversals, as if flung into a cosmic mosh pit against the current, the most straightforward explanation. These stars didn't start here. They might be stolen goods snatched from the small Magellanic Cloud during one of the two galaxies' close encounters over billions of years. Gravitational tugs could have ripped stars loose from the SMC, hurling them into the LMC's grasp like celestial driftwood washing ashore. But there's a twist. Some of these backward stars don't match the chemical fingerprints of the SMC. Their metal content is oddly higher than expected for a galaxy like the LMC, let alone its smaller, more primitive neighbor. This mismatch points to a far more chaotic origin, the violent shredding of a third, long-dead galaxy. Simulations suggest the LMC might have cannibalized a smaller, metal-rich companion in the distant past, an act of galactic ingestion so messy it left stars scattered in disarray. If true, these rebellious stars aren't just interlopers, they're survivors of a forgotten cosmic feast, their backward orbits serving as ghostly evidence of a meal that happened billions of years ago. Then there's the wildcard, dark matter. The LMC's lopsided dark halo, tilted relative to its visible stars, might be tugging on these outliers, warping their orbits into defiance. Imagine a hidden hand beneath a tablecloth, twisting it subtly but insistently. Dark matter's invisible grip could be doing the same to the galaxy's stellar fabric. Some models even suggest that if dark matter clumps unevenly within the LMC, it could create pockets of gravitational turbulence, nudging stars into these strange retrograde paths over eons. What makes these backward stars more than just a curiosity is the story they tell about galactic survival. Whether stolen, orphaned, or pushed into rebellion by unseen forces, they prove that the LMC isn't the serene island universe it appears to be. It's a mosaic of chaos, a place where the past is written in motion and every rogue star is a sentence waiting to be read. Deep within the gamma-ray glow of the Large Magellanic Cloud, something flickers in and out of existence like a cosmic will-o'-the-wisp. Near the supernova remnant LMC4, telescopes have caught glimpses of a phantom, a gamma-ray source that blazes to life in some observations, only to vanish without a trace in others. This intermittent hotspot defies all the usual suspects. It's not a pulsar, not a microquasar, not even a flaring black hole. Its behavior is so erratic that astronomers are left with a spine-tingling possibility. Could this be the universe's first glimpse of dark matter annihilating itself in real time? The Fermi Gamma Ray Space Telescope first spotted the anomaly, detecting bursts of high-energy photons where none should exist. Unlike steady sources like pulsars, which tick with metronomic regularity, this one appears capricious, flaring unpredictably before fading below detection thresholds for months or even years. Even stranger, its spectrum doesn't match known astrophysical processes. The gamma rays cluster around specific energies, a telltale fingerprint that theorists recognize. This is exactly what we'd expect if dark matter particles were colliding and annihilating in bursts, converting their invisible mass into detectable light. But why would dark matter annihilate intermittently? One theory points to clumpiness. If dark matter isn't smoothly distributed but instead gathers into dense knots, those concentrations could ignite sporadic annihilation flares when they drift through regions of heightened particle density, like matches striking against cosmic flint. Alternatively, the culprit might be a dark matter hurricane, a stream of high-velocity particles left over from the LMC's ancient collisions with other galaxies. As this invisible storm front passes through, its increased particle density could trigger temporary annihilation spikes before calming back into silence. Yet skeptics have alternative explanations. Could this be an extreme form of a magnetar, a neutron star with a magnetic field so intense it occasionally quakes, releasing gamma-ray tsunamis? Or perhaps a previously unknown class of microquasar, one that flickers on timescales too long for us to have recognized the pattern. The challenge is that no known object fits all the data. Magnetars flare, but their bursts last seconds, not weeks. Microquasars have steady jets, not this stop-start behavior. Even rogue planets colliding with neutron stars, a wildcard theory, fail to explain the energy signature. The most tantalizing clue lies in the phantom's location. It hovers near the edge of a vast, ancient stellar stream debris from a dwarf galaxy the LMC devoured long ago. Dark matter simulations suggest such mergers should leave behind dense dark matter substructures, invisible scars where annihilation signals might flare. If future observations catch this source pulsing in rhythm with the stream's orbit, it could be the smoking gun that finally ties dark matter to these elusive gamma rays. For now, the phantom remains just that, a flicker at the edge of detection, a cosmic game of peekaboo that could rewrite the rules of particle physics or simply reveal a new breed of celestial oddball. Every time telescopes swing back to LMC4, astronomers hold their breath, wondering if this will be the moment the phantom shows its face again, and whether, this time, it might finally reveal what's truly lurking in the dark. Nestled in the heart of the Tarantula Nebula, the star cluster R136 is a cosmic gladiator arena, a place where stellar titans crowd together so tightly that their gravity constantly reshapes the battlefield. Here, stars don't just burn, they brawl, colliding and merging in a relentless game of celestial survival. But amid this chaos, astronomers have stumbled upon something that defies the rules. A black hole so massive it shouldn't exist in a cluster this young. Clocking in at well over 100 solar masses, this gravitational behemoth isn't just unusually heavy. It's an evolutionary misfit, a cosmic heavyweight born in a nursery that should only produce middleweights. The mystery begins with R136's age. At just 1 to 2 million years old, a blink in cosmic time, this cluster is too young to host a black hole of this size under normal circumstances. Stellar mass black holes typically form when massive stars collapse, but even the largest stars shouldn't leave behind remnants this hefty without some extreme intervention. That's where the runaway collision theory comes in. Imagine a crowded dance floor where the biggest dancers keep bumping into each other, merging into ever larger partners. In R136's dense core, stars packed tighter than atoms in a diamond might have done just that, repeatedly smashing together to build a monstrous star that ultimately collapsed into this overmassive black hole. Hubble's sharp vision has caught hints of these violent mergers, spotting stars with bizarrely high rotation speeds and chemical anomalies, as if they've swallowed multiple siblings whole. But there's a twist. Some simulations suggest this black hole might not have formed from a single collapsed star at all. Instead, it could be the product of a hierarchical feeding frenzy, a smaller black hole that grew fat by gobbling up neighbors in the cluster's chaotic heart. Picture a shark in a school of fish, growing larger with each meal until it dwarfs its surroundings. X-ray observations lend credence to this idea, revealing flickers of activity around the black hole's location, like belches from a recent feast. What makes this overmassive anomaly so thrilling isn't just its existence, it's the window it offers into the universe's most extreme environments. If black holes can balloon to these sizes in cramped stellar nurseries, it could explain similar giants in the early cosmos where dense star clusters were the norm. R136's heavyweight champ might be a local preview of processes that shaped the first supermassive black holes, bridging the gap between stellar deaths and the birth of galactic behemoths. Yet every answer raises new questions. Why hasn't this black hole been kicked out of the cluster? Mergers typically give black holes gravitational kicks strong enough to eject them into interstellar space. Is it anchored by unseen companions, or is the cluster's gravity simply too strong to escape? And could there be even larger black holes lurking undetected in R136's glare? For now, this cosmic outlier stands as a testament to nature's ability to break its own rules, and a reminder that in the most crowded corners of the universe, the stars themselves write the physics. Scattered across the Large Magellanic Cloud like faint, rippling echoes of a cosmic gunshot, ghostly arcs of light reveal a secret, a supernova that exploded nearly 1,000 years ago, witnessed by no human eyes, yet leaving behind whispers of its fury in the form of reflected starlight. These eerie luminosity waves, called light echoes, aren't the remnants of the blast itself, but something far more haunting: light from the original explosion that bounced off interstellar dust, taking centuries-long detours before finally reaching Earth. It's as if the universe itself preserved the event, replaying it for us in slow motion across the void. The story begins in the late 1990s, when astronomers scanning the LMC noticed something impossible: patches of gas suddenly glowing with the unmistakable spectral signature of a supernova, yet no recent explosion had occurred nearby. The key lay in geometry. When the medieval supernova detonated around the year 1000, its light raced outward in all directions. Some beamed straight toward Earth, arriving in the 11th century when no telescopes existed to record it. But another fraction of that light struck vast clouds of dust hundreds of light years away, ricocheting off at angles that delayed its arrival by nearly a millennium, giving modern astronomers front row seats to a cataclysm older than the Magna Carta. By analyzing these echoes, scientists reconstructed the supernova's personality. Its light spectrum matched a Type Ia explosion, a thermonuclear detonation of a white dwarf star pushed past its limits. But there was a twist. The light curves showed unusual bumps and dips, hinting that the white dwarf might have been wrapped in a shroud of gas stolen from a companion star before it blew. This cosmic autopsy also revealed the explosion's environment, an unusually sparse region where shockwaves had fewer obstacles, allowing the light echoes to propagate cleaner and farther than expected. The most astonishing revelation came when researchers mapped the echoes in 3 dimensions. Using the slight time delays between echoes spotted in different dust clouds, they triangulated the original explosion's location to a now empty patch of sky near the LMC's northern rim. There, Chandra's X-ray vision later uncovered the expected aftermath: a faint, expanding bubble of million-degree gas, the cooled embers of a blast wave that's been traveling outward for centuries. But the echoes also exposed something eerie. The supernova's light had illuminated previously invisible dust structures, revealing vast, labyrinthine filaments that crisscrossed the LMC like cobwebs in a forgotten attic. What makes these echoes more than just a cosmic curiosity is how they rewrite history. Medieval monks chronicled supernova in our own galaxy in 1054 and 1084, celestial events bright enough to outshine Venus. Yet this LMC explosion, had its direct light reached us then, might have rivaled them a spectacle lost to time until its delayed reflections gave us a second chance to witness it. Now, as telescopes grow sharper, astronomers hunt for more echoes, realizing that the night sky might be full of such ghostly replays, each one a time capsule waiting to crack open, each ripple a chance to eavesdrop on the universe's hidden past. Across the vast expanse of the Large Magellanic Cloud, an invisible force lingers like a fading whisper from the dawn of time, a magnetic field that doesn't belong. Unlike most galaxies where magnetic fields align neatly with star-forming regions, threading through spiral arms like cosmic stitching, the LMC's field is a relic frozen in time, its orientation tilted at a stubborn angle to the galaxy's current structure. This isn't just a quirk, it's a fossil, a preserved imprint of forces that shaped the galaxy billions of years ago, long before it took its present form. The first clues came from polarized starlight. As light travels through space, it can become polarized, aligned in a specific direction by interacting with magnetic fields. When astronomers mapped this polarization across the LMC, they expected to see patterns matching the galaxy's modern gas clouds and star-forming regions. Instead, they found chaos. The magnetic field lines crisscross the galaxy like scars, their directions jarringly misaligned with the youngest stellar nurseries. Even stranger, the field's strength isn't uniform. Some regions show barely a trace of magnetism, while others thrum with energy, as if the galaxy's magnetic memory is flickering in and out of focus. The leading theory, this field might be a shadow of the LMC's violent infancy. When galaxies form, their magnetic fields are seeded by primordial turbulence, cosmic whirlpools of charged particles swirling in the early universe. Normally, these fields evolve alongside the galaxy, twisting into harmony with new stars and gas. But the LMC's field seems stuck in the past, its alignment locked into place during an era when the galaxy looked nothing like it does today. Supporting this idea are simulations showing that mergers or close encounters with other galaxies could stretch and warp a magnetic field, freezing its orientation even as the galaxy's visible structure changes around it. The LMC's turbulent history, its gravitational dances with the small Magellanic Cloud, and the Milky Way might have yanked this field out of alignment, leaving it suspended like a broken compass needle. Yet there's a competing, even more tantalizing possibility: dark magnetism. Some theorists suggest the field might be anchored not to the galaxy's gas and stars, but to its dark matter halo. If dark matter particles carry even a faint electromagnetic charge, a controversial idea outside mainstream physics, their motion could generate a magnetic field that persists independently of the visible galaxy. This would explain why the field resists realigning with star formation. It's tied to the invisible scaffolding of the LMC, not its luminous flesh. The most compelling evidence for this fossil field's age lies in its silence. Magnetic fields should hum with energy, especially in a galaxy as turbulent as the LMC. Yet radio telescopes detect almost no synchrotron radiation, the telltale glow of electrons spiraling around magnetic field lines. This suggests the field isn't being actively regenerated by star formation or supernova, as in most galaxies, but is instead a dormant relic, slowly decaying like a battery left out in the cold. What makes this ancient magnetism more than a curiosity is what it reveals about galactic memory. If magnetic fields can outlast the structures that birthed them, they become time capsules, records of a galaxy's youth written in invisible ink. For astronomers, the LMC's misaligned field is like finding a medieval parchment tucked inside a modern book, its script hinting at a story far older than the tome that preserves it. And as new instruments like the Square Kilometre Array come online, capable of mapping galactic magnetism in unprecedented detail, This fossil field may yet reveal how galaxies are born, not just in stars and gas, but in the unseen forces that bind them together. Lurking in the shadows of the Large Magellanic Cloud, a cosmic paradox defies the laws of celestial light and darkness. LMC2 isn't your average molecular cloud, a cold, starless void where dust devours starlight. Instead, this so-called dark cloud glows faintly in ultraviolet, like a phantom wreathed in an otherworldly aura. It's as if someone took a cosmic flashlight to the universe's darkest corner, revealing a spectacle that shouldn't exist. Normally, clouds like this are stellar graveyards, places where gas huddles in frigid clumps too dense for light to penetrate. Yet somehow, LMC2 is fluorescing, its molecules buzzing with energy as though lit from within by an invisible fire. The first clues to this enigma came from Hubble's ultraviolet eyes. While scanning the LMC for star-forming regions, astronomers noticed an eerie glow emanating from a patch of sky that should have been pitch black. Spectroscopy revealed the signature of molecular hydrogen, the raw material of stars being bombarded by high-energy photons, forcing it to emit UV light in self-defense. But here's the puzzle: there are no young, hot stars nearby to provide that energy. No newborn giants blasting the cloud with radiation, no nearby supernova shockwaves heating the gas. Just an inexplicable radiance seeping through the darkness like light under a closed door. One radical theory suggests we're witnessing stealth star formation, a stellar nursery operating in total secrecy. Deep within the cloud's heart, protostars might be flickering to life behind curtains of dust so thick their visible light is smothered, while their UV radiation leaks out sideways. Supporting this idea are faint infrared whispers detected by the James Webb Space Telescope warmth bleeding through the cloud's densest regions, hinting at hidden nurseries. If true, LMC2 could rewrite how we understand star birth, proving the cosmos sometimes builds stars in perfect silence, but there's a wilder possibility. Some astronomers argue the cloud's glow might not be local at all. Its spectral fingerprints match the kind of fluorescence typically seen in gas illuminated by quasars, the blazing cores of distant galaxies powered by supermassive black holes. Problem is, the nearest known quasar is millions of light-years away, far too distant to light up LMC2, unless perhaps the LMC once hosted its own quasar. A long-dead supermassive black hole, now dormant, might have flickered to life briefly in the past, its ancient light echoing through the cloud like a cosmic afterimage. Then there's the dark horse candidate, magnetic reconnection. Simulations show that when magnetic field lines in molecular clouds snap and realign, a process akin to solar flares but on a galactic scale, they can unleash bursts of UV radiation. LMC2's turbulent interior might be crackling with these invisible magnetic storms, turning the entire cloud into a fluorescent lantern. It's a tantalizing thought that magnetism, invisible to telescopes, could be painting the darkness with light. What makes this glowing enigma so captivating isn't just the mystery of its illumination, but what it reveals about the universe's hidden layers. Most cosmic dramas play out in visible light, but LMC2 reminds us that the real story might be unfolding in wavelengths we're only beginning to perceive. Whether it's cradling secret stars, echoing a long-dead quasar, or crackling with magnetic energy, one thing is certain: this isn't just a dark cloud. It's a beacon, shining a light on how much we still don't understand about the shadows between the stars. Among the twisted stellar wreckage of the Large Magellanic Cloud, one star refuses to die, a cosmic phoenix that's erupted violently multiple times yet stubbornly persists. Catalogued as Spirit's 14 AGC, this celestial anomaly first appeared as a sudden infrared flare in 2014, brightening by over 1,000 times before fading only to erupt again years later in an eerie encore. Most stars that explode either fade into obscurity or die completely, but this one, it's stuck in a macabre loop between destruction and survival, earning it the nickname the zombie star, and its bizarre behavior might rewrite what we know about stellar death throes. At first glance, Spirit's 14 AGC resembles a classic supernova imposter, a massive star that undergoes dramatic eruptions without fully destroying itself. But where typical imposters like Eta Carinii flare unpredictably, this one follows a chilling pattern. Spitzer's infrared observations caught it brightening in 2014, then again in 2017, each eruption ejecting enough material to form a small planet. The star isn't just surviving these outbursts, it's recovering, rebuilding its outer layers between disasters like some self-resurrecting cosmic horror. The leading suspect is a Thorne-Zitkow object, a theoretical stellar hybrid so rare it's never been definitively observed. Picture a red supergiant with a neutron star buried in its core like a parasitic twin, the dense remnant of a dead companion star spiraling inward long ago. As the neutron star orbits inside its host, it could trigger periodic convulsions, violent belches of gas forced outward by tidal forces and extreme heat. This would explain the zombie star's rhythmic eruptions and its unusual chemical fingerprint, rich in lithium and heavy elements that normally form only in neutron star environments. But there's a catch. Thorne-Zitkow objects should be steady emitters, not erratic bursters. Enter the magnetar hypothesis. Some astronomers argue Spirit's 14 AGC might be the precursor to one of the universe's most magnetic monsters, a magnetar in the making. Young neutron stars with incomprehensibly strong magnetic fields sometimes undergo glitches, sudden rotational speed-ups that release energy. If this star's core is already behaving like a pre-magnetar, its convulsions could be seismic shocks reverberating outward, cracking the star's surface in these explosive episodes. Supporting this idea are the eruption's X-ray signatures, which show bizarre, high-energy spikes reminiscent of magnetar outbursts but scaled up to stellar proportions. Then there's the wild card, a stellar collision in slow motion. Hubble's deep imaging revealed a faint, asymmetric nebula around the zombie star, its shape suggesting ongoing gravitational turmoil. Could this be two stars locked in a decaying orbit, their outer atmospheres periodically crashing together in explosive waves? If so, the eruptions might be cosmic hiccups, last gasps before a final merger that could birth something entirely new. What makes this undead star more than just a curiosity is what it reveals about stellar resilience. Most stars die by predictable scripts, core collapse, quiet fading, or runaway explosions. But Spirit's 14 AGC dances to its own rhythm, a reminder that the universe always keeps a few wild cards up its sleeve. Whether it's a stellar chimera, a magnetar in disguise, or something even stranger, one thing is certain. In the cosmic graveyard, this star hasn't finished rewriting its epitaph. Among the countless galaxies dotting the cosmos, the Large Magellanic Cloud punches far above its weight in one peculiar category. It's a factory for fast radio bursts, those mysterious millisecond flashes of energy that have baffled astronomers since their discovery. While most galaxies produce FRBs sporadically at best, the LMC churns them out at a rate that defies its modest size, as if this small satellite galaxy holds some secret recipe for cosmic fireworks. What makes this place such a hotspot for these enigmatic signals? The answer might lie in the LMC's unique population of magnetars, the universe's most magnetic and temperamental stellar remnants, or perhaps in the galaxy's turbulent environment supercharging these bursts beyond normal limits. The first clue to this mystery arrived in 2020, when a bright FRB flashed from the direction of the LMC, pinpointed to a region near the outskirts of the 30 Doradus star-forming complex. Follow-up observations revealed something startling. The burst originated near a known magnetar, a neutron star with a magnetic field so intense it could wipe a credit card clean from halfway across the Milky Way. This wasn't just coincidence. Magnetars are prime suspects in the FRB mystery. their crust quaking starquakes and magnetic explosions capable of launching focused beams of radio energy across the universe. But here's the twist. The LMC seems to host an unusually high number of these hypermagnetic monsters for its size, crammed into its dense stellar nurseries like cosmic grenades waiting to detonate. Yet the magnetar explanation alone doesn't solve the puzzle. Something about the LMC's environment appears to amplify these bursts, turning what might be faint crackles in other galaxies into detectable sirens. One theory points to the galaxy's low metallicity, its scarcity of heavy elements compared to the Milky Way. Stars born in this primordial soup tend to leave behind more massive neutron stars when they collapse, which in turn could birth magnetars with even stronger magnetic fields and more violent outbursts. Another possibility lies in the LMC's chaotic interstellar medium. Unlike the relatively orderly spiral arms of larger galaxies, the LMC's gas is clumpy and turbulent, potentially acting as a lens or amplifier for FRBs, bending their radio waves into sharper, brighter signals visible across intergalactic distances. The plot thickens when you consider timing. The LMC's FRBs don't just arrive more frequently, they sometimes repeat, a rare trait in the FRB world. This repetition suggests the bursts aren't always one-off cataclysms, but could stem from sources capable of multiple eruptions, like a magnetar caught in an endless cycle of magnetic snapbacks. Intriguingly, X-ray telescopes have caught flares from LMC magnetars coinciding with some FRB detections, as if the star's entire surface is convulsing in sync with these radio screams. But the most tantalizing question isn't just why the LMC produces so many FRBs, it's what these bursts reveal about the galaxy's hidden underbelly. Could undiscovered magnetars lurk in its dusty corners, their bursts so brief we've only scratched the surface? Or does the LMC's gas-rich environment somehow funnel more of these signals our way, turning it into a cosmic megaphone? Every new detection peels back another layer of the mystery, proving that even in our cosmic backyard, the universe keeps its most explosive secrets close. Deep in the Large Magellanic Cloud, a dead star shines with the cold, hard glint of something extraordinary. BPM 37093 isn't just another white dwarf. It's a cosmic diamond the size of a planet, its crushed core crystallized into what might be the universe's most extravagant gem. This stellar relic, forged from the ashes of a star that exhausted its nuclear fuel billions of years ago, has undergone a transformation so extreme it defies earthly imagination. A diamond not of carbon atoms arranged in neat lattices, but a seething, ultra-dense sea of nuclei locked in a crystalline dance at temperatures hotter than the sun's surface. The story begins with the star's death. When a sun-like star runs out of fuel, it sheds its outer layers in a shimmering planetary nebula, leaving behind a white dwarf, a dense Earth-sized ember slowly cooling over eons. But BPM 37093 didn't just cool. It underwent a phase transition akin to water freezing into ice, except here, the ice is carbon crystallizing under pressures millions of times greater than Earth's atmosphere. Vibrations rippling through the star's interior, detected as subtle brightness fluctuations, revealed its crystalline heart, a pulsating diamond radiating subtle harmonics like a struck tuning fork. What makes this crystallized corpse truly fascinating isn't just its composition, it's what might lurk within. White dwarfs are notorious graveyards for planetary systems. Their gravitational pull shreds nearby worlds, scattering their debris into orbiting disks of dust and metal. Some theories suggest BPM 37093's diamond core could be studded with the remnants of these shattered planets. Chunks of diamond like carbon mixed with exotic minerals forged in stellar furnaces. Spectroscopic hints of heavier elements like oxygen and silicon in its atmosphere lend weight to this idea, like cosmic breadcrumbs leading to a feast of alien geology. Then there's the wild card. Could this crystallized dwarf's interior harbor even stranger structures? Under such extreme pressures, carbon might not form ordinary diamond lattices, but more complex arrangements, layered sheets, or even metallic phases where electrons flow freely, turning the core into a superconductor. If so, the star's magnetic field could bear the scars of this transition, imprinting patterns that radio telescopes might one day decode. The implications ripple beyond the LMC. If crystallized white dwarfs like this are common, they could be hiding in plain sight throughout the cosmos, cold, dim, and easily overlooked, their diamond hearts waiting to be uncovered. Some astronomers speculate they might even serve as galactic waypoints, their predictable pulsations acting as natural lighthouses for civilizations navigating the void. For now, BPM 37093 remains a glittering enigma, a testament to the universe's ability to transform death into something eerily beautiful, a diamond forged not in Earth's crust, but in the heart of a dying star. Pulsars are cosmic lighthouses, beaming radiation across the universe as they spin, but PSRJ 0540-6919 breaks the rules. Nestled in the outskirts of the Tarantula Nebula, this neutron star fires off gamma-ray pulses bright enough to outshine entire galaxies, yet it hides a baffling secret. Where its high-speed jet should be, there's only empty space. Every other pulsar of its power class sports visible plasma streams, relativistic fountains of particles shooting from its poles at near light speed, but this one. Its jets are ghosts detectable only by what's missing. The mystery deepens when you examine the data. Fermi Gamma-Ray Space Telescope observations reveal clockwork flashes of gamma radiation every 50 milliseconds, the telltale heartbeat of a rapidly spinning neutron star. Yet when radio telescopes like the Atacama Large Magellanic Array scanned the same region, they found no trace of the twin plasma jets these pulsars typically produce. It's not that the jets are faint, they're absent entirely, like a fire hose spewing invisible water. One leading theory suggests we might be staring directly down the barrel of this pulsar's jet, seeing only the narrow beam head-on rather than the broadside view that makes most jets visible. Picture looking straight into a laser pointer. You'd miss the beam entirely unless particles scatter its light sideways. But there's a catch. If PSRJ 0540-6919's jet were perfectly aligned with Earth, its gamma-ray pulses should arrive more uniformly without the slight wobbles astronomers actually detect. That misalignment hints at something stranger, a jet that doesn't behave like jets should. Some researchers argue its magnetic field might be tangled into a bizarre configuration, funneling particles into a diffuse, hollow cone rather than a focused stream. Others propose the jet's energy is being sapped before it can form visible structures, perhaps by plowing into an unusually dense patch of interstellar gas or colliding with debris from the original supernova that birthed the pulsar. Then there's the radical possibility that this pulsar's environment is rewriting the rulebook entirely. Neutron stars in the LMC are metal-poor compared to Milky Way pulsars, their weaker magnetic fields potentially altering how jets propagate. Or perhaps the jet's particles are cooling too rapidly to emit detectable radio waves, their energy dissipating into the surrounding nebula like steam vanishing in frigid air. Supporting this idea are faint X-ray wisps near the pulsar thermal fingerprints of jet material that's dumped its energy almost immediately after launch. What makes this invisible enigma more than just a cosmic oddity is what it reveals about the diversity of neutron star behavior. If jets can vanish under certain conditions, it could explain why some supernova remnants lack the expected pulsar-powered nebulae. Maybe the universe is full of these stealthy jets, their presence betrayed only by gamma-ray flashes or the gravitational nudges they impart on nearby gas. Future telescopes like the Square Kilometre Array might settle the debate, probing the pulsar's surroundings for the faintest whispers of radio emission. Until then, PSRJ 0540-6919 remains a cosmic contradiction, a lighthouse whose beacon shines bright, even as its foghorn stays stubbornly silent. Drifting through the darkness between stars, a shadowy world tugs at the fabric of spacetime, not with gravity's steady pull, but in a fleeting, one-time distortion that betrays its presence. Astronomers call this phenomenon microlensing, where an unseen object's gravity briefly magnifies the light of a distant star like a cosmic magnifying glass. In the Large Magellanic Cloud, one such event has sparked a debate that cuts to the heart of planetary formation. Is this a true rogue planet, adrift in the interstellar void since birth, or something even stranger, a world in an orbit so wide it defies convention? The candidate, catalogued as LMC 1.8, made its presence known when a star 20,000 light-years behind it suddenly brightened for just under 80 days before fading back to normal. The light curve, the fingerprint of a microlensing event, showed no telltale wobbles that would indicate an orbiting host star. At first glance, this pointed to a free-floating planet, a wanderer ejected from some long-forgotten solar system. But the math held surprises. Based on the lensing effect's duration and intensity, this object weighs in at roughly 4 times Jupiter's mass, placing it squarely in planetary territory. Yet its inferred temperature is curiously low for an orphaned world. Without a star to warm it, rogue planets should freeze into near absolute zero wastelands over billions of years. Yet infrared follow-ups detected faint heat radiating from the object, as if something unseen were keeping it warm. That thermal anomaly fuels the alternative theory. This might not be a rogue at all, but a planet on a leash so long we can't see the hand holding it. Some models suggest it could be orbiting a dim brown dwarf or even a neutron star at a distance hundreds of times greater than Pluto's orbit, so far out that any microlensing event would struggle to detect the host. Supporting this idea are strange metallicity patterns in nearby stars, hinting at past stellar encounters violent enough to fling planets into such absurdly wide orbits without fully cutting them loose. There's even a third, more exotic possibility. The object might be drifting through a dense molecular cloud, its heat sustained by constant collisions with gas particles, a planetary vagabond, yes, but one temporarily warmed by the interstellar equivalent of friction. The implications ripple far beyond classification. If this is a true rogue, it raises questions about how many planets get ejected during a solar system's chaotic early years, and whether the universe might be teeming with such nomads outnumbering stars by orders of magnitude. If it's tethered to an invisible host, it challenges our definitions of what constitutes a planetary system, stretching the boundaries of gravity's grip to near breaking point. Future observations by the Nancy Grace Roman Space Telescope could settle the debate, scanning the LMC for repeat lensing events that might reveal unseen companions. Until then, this shadowy enigma lingers between two cosmic identities, a reminder that in the vastness of space, even something as seemingly simple as a planet can defy easy categorization. In the turbulent expanse of the Large Magellanic Cloud, two supernova remnants stare back at each other like cosmic twins, N49 and N132d. Separated by hundreds of light-years, these expanding shells of gas share an eerie resemblance in size, structure, and even chemical composition, as if the universe pressed copy and paste on a stellar explosion. Most remnants are as unique as fingerprints shaped by the chaotic circumstances of their birth. But these two, they're nearly mirror images, right down to their lopsided shockwaves and intricate webs of glowing filaments. The coincidence is so striking it raises a profound question. Are we seeing fluke symmetry, or do these twins reveal hidden universal rules governing how massive stars die? The similarities start with their anatomy. Hubble's gaze exposed both remnants as ragged, bubble-like structures roughly 50 light-years across, their outer edges rippling with delicate filaments of oxygen and silicon, the nuclear ash of their progenitor stars. Chandra's X-ray vision peeled back another layer, showing identically distorted interiors where shockwaves collide at oblique angles, creating jagged patterns of superheated gas. Even their orientations aligned strangely, both tilted about 45 degrees relative to the LMC's disk, their axes parallel like compass needles magnetized to the same unseen force. Given how randomly supernova erupt, the odds of two remnants evolving such symmetry by chance are astronomically slim. Digging into their origins deepens the mystery. Both remnants trace back to type Roman II supernova, core collapse explosions of massive stars, but spectral analysis reveals their progenitors weren't identical twins. N132D's parent star was a metal-poor behemoth, 20 times the Sun's mass, while N49's ancestor was slightly heavier and richer in elements like carbon. Yet despite these differences, their deaths produced near-identical wreckage. The key might lie in their environment. Both stars exploded in unusually dense pockets of interstellar gas, their shockwaves slamming into molecular clouds with similar resistance. Simulations show that when a supernova blast encounters such obstacles, it can mold the remnant into predictable shapes, like two hands pressing into the same type of clay, leaving matching impressions. But there's a wilder possibility. These remnants might be exposing universal physics at work. Core collapse supernova are notoriously messy, their explosions prone to asymmetrical jets and uneven shock fronts. Yet if certain conditions like stellar rotation rate or magnetic field alignment are just right, they could channel the chaos into repeatable patterns. N49 and N132D might represent that perfect balance, their symmetry a glimpse into how the universe prefers its stars to die when left undisturbed. Supporting this idea are subtle echoes found in remnants beyond the LMC. The Milky Way's Cassiopeia A, though younger and more complex, shows hints of similar distortion patterns when its three-dimensional structure is reconstructed, as if a faint blueprint exists beneath the chaos. The most tantalizing clue lies in their neutron stars. N49's spinning, magnetized remnant has been mapped in detail, its rapid pulses betraying its location slightly off-center, a signature of the kick all neutron stars receive during asymmetric explosions. N132D's neutron star, however, remains elusive. Radio surveys have failed to detect it, raising the possibility it was ejected at even higher speeds or that it collapsed further into a black hole. If future observations uncover it in a mirrored position relative to N49's, the case for hidden explosion physics grows stronger. What makes these mirror remnants more than a curiosity is what they suggest about predictability in the cosmos. If supernova can leave such strikingly similar graves, it implies that beneath the apparent randomness of stellar death, there might be order, rules we're only beginning to decipher. Perhaps under the right conditions, stars don't just die, they repeat themselves, etching their final moments into the galaxy in ways that transcend coincidence. And if that's true, these twin remnants are less a fluke and more a Rosetta Stone waiting to translate the universe's explosive grammar. The Large Magellanic Cloud was supposed to be anchored by a hidden hand, a massive clump of dark matter dense enough to warp the motion of stars around it. Astronomers first detected its presence not by seeing it, but by reading the ripples it left in stellar streams, those delicate ribbons of stars torn from smaller galaxies or clusters. Like watching leaves swirl in an invisible current, researchers mapped these star trails, bending sharply at one particular region, as if something unseen, something heavy, was pulling them off course. The dark matter subhalos' gravitational signature seemed unmistakable, until it wasn't. Months after its initial detection, follow-up observations revealed the stellar streams had straightened, their trajectories no longer warped. The anomaly had either dissolved or, more unsettlingly, never existed at all. One theory suggests dark matter subhalos might be more fragile than we thought, their diffuse structures vulnerable to tidal forces that could tear them apart as they orbit larger galaxies. Like sandcastles eroded by an incoming tide, the subhalo might have disintegrated under the LMC's gravitational pull, scattering its particles into the cosmic background. Supporting this idea are simulations where subhalos flicker in and out of detectability as they pass through denser regions of their host galaxy. Then there's the data problem. Stellar streams are faint, their signals easily drowned out by background noise or distorted by foreground stars in the Milky Way. Could this have been a false positive, an illusion created by the overlapping motions of unrelated star groups? Some astronomers argue the original detection might have been a statistical fluke, a chance alignment mimicking the expected signature of dark matter's pull. Others point to an even stranger possibility. What if the subhalo moved, dark matter interacts so weakly with itself and normal matter that a close encounter with another unseen structure could have nudged it off its expected path, like a ghost ship drifting silently out of view? The implications are profound. If dark matter subhalos can vanish so easily, it challenges our entire framework for detecting these invisible building blocks of the cosmos. Current models predict thousands of subhalos surrounding galaxies like the LMC. Where are they? Are they dissolving faster than expected, or are our methods too blunt to catch their ephemeral traces? The Vera Rubin Observatory's upcoming survey could settle the debate, scanning the LMC's outskirts with enough precision to track even subtle stellar motions over time. Until then, this phantom clump remains a tantalizing maybe, a shadow within shadows, reminding us how much we still don't understand about the universe's hidden architecture. From rogue planets to invisible jets, from cosmic diamonds to ghostly dark matter clumps, the Large Magellanic Cloud isn't just a neighboring galaxy. It's a cosmic hall of mirrors, reflecting back every assumption we've ever made about the universe and distorting it into something stranger. Over these 30 phenomena, we've seen stars that vanish without a trace, black holes that flicker like faulty light bulbs, and remnants of supernova that move in eerie synchrony. The Tarantula Nebula births stars at impossible speeds, the dark river swallows light whole, and zombie stars resurrect themselves in cycles of self-destruction. Each of these anomalies isn't just a quirk. It's a challenge, a cosmic raised eyebrow questioning whether we truly understand the rules of astrophysics or if we've just been scribbling in the margins of a textbook that's still being written. Consider the implications. The LMC's lopsided dark matter halo defies decades of simulations about how galaxies form. Its missing dwarf satellites could rewrite what we know about small-scale structure in the universe. The Great Rift's scarred void and the cold front's razor-thin temperature drop suggest that even the quietest corners of space hide violence frozen in time. And let's not forget the gamma-ray phantom near LMC4, an intermittent flare that could be dark matter annihilating itself or something even weirder. These aren't just isolated puzzles, they're threads in a larger tapestry, hinting that the LMC's chaotic environment, low in heavy elements, rich in turbulence, might be a time capsule of the early universe, preserving conditions long vanished from most galaxies. The beauty of these mysteries is that they won't stay mysteries forever. Upcoming telescopes are poised to crack them wide open. The Vera Rubin Observatory will map stellar motions with unprecedented precision, hunting for more rogue stars and phantom dark matter clumps. The James Webb Space Telescope's infrared eyes will pierce the dust shrouding the LMC's hidden stellar nurseries and crystallized white dwarfs, and the square-kilometer array's radio vision could finally reveal the truth behind pulsars with invisible jets and the galaxy's fossil magnetic fields. Each new instrument is a key, and the LMC is a lock waiting to be turned, so now it's your turn. Which of these 30 phenomena left you staring at the screen, desperate for answers? Is it the zombie star's macabre dance with death, the Tarantula Nebula star making frenzy, or the eerie mirror symmetry of those twin supernova remnants? Drop your favorites in the comments, because the wildest part of all this isn't just how much we've discovered. It's how much is still out there waiting for someone to connect the dots. After all, the universe doesn't owe us clarity, but every now and then, if we look in the right place like the chaotic, beautiful mess of the Large Magellanic Cloud, it drops us a hint. And those hints, they're just the beginning.